Good morning, everyone. Today I'm going to talk about design of analog filters. Before I start, let me share my screen. I hope my screen is visible. Okay, so design of analog filters. So the first analog filter which we are going to discuss is Butterworth filter. So the title there is analog Butterworth filters. So the magnitude square response of an nth order Butterworth low pass filter is given by, this is the expression, h of subscript is A stands for analog, okay, j omega magnitude square is equal to 1 divided by 1 plus omega. So we call this as a continuous omega divided by omega c to the power of 2n. So omega c is called as a cutoff frequency, which is in units as radians per second, and n is the filter order. Okay, so let's try to analyze based on this magnitude square response by putting in a different values of continuous omega and try to see whether this looks like a low pass filter shape. So what I'm going to do here is I'm going to put omega is equal to 0. If I put omega is equal to 0, the magnitude square response is going to be 1. When omega is equal to omega c, so this is going to be 1, so this is half. Okay, when omega tends to infinity, so if this is infinity, so the entire denominator term would go to infinity, so the magnitude square is going to be 0. So it means that at omega equal to 0, the magnitude square is 1. At omega is equal to omega c, it is half. Omega tends is equal to infinity, it is going to be 0. So it is more like a low pass filter characteristics. Okay. So let's try to understand a little bit more on the cutoff frequency aspect. Okay. So the cutoff frequency, omega c, corresponds to the half power. Why it is called as a half power is because this is nothing but the power magnitude square. So this is half, so we call it as a half power, or 3 dB attenuation of the magnitude response. 3 dB attenuation of the magnitude response, meaning that, so if I take 20 log 10 of this value, then it is going to be minus 3 dB point. Minus is nothing but attenuation, so that's why it is called as a 3 dB attenuation point. Okay, so just as a schematic of how this magnitude response looks like, as you magnitude square response looks like as you vary the filter order. Okay, so x-axis here is omega and the y-axis is a magnitude square. So clearly what you can see here is, so here different color represents the different filter order. So for all the filter order, the value is going to be 1 at omega equal to 0. For all the filter order at omega equal to omega c, the magnitude square in this case would be equal to half. And then these are the two common points. And afterwards, what you can see here is that if you take n is equal to 1, which is a lower filter order, the response looks like this. Okay, as opposed to when you take n is equal to 100, the slope here is lot sharper. If the slope is lot sharper, as you increase the filter order, then it is coming closer to the ideal representation of a low pass filter. Technically speaking, when n tends to infinity, this looks like an ideal filter. Okay, so what this suggests to us is that in order to get a better representation of an ideal low pass filter, we need to increase the filter order. But again, at the other caveat is, it is fine to increase the filter order, but increasing the filter order would increase the number of computational complexity. And if you want to implement them in a hardware, like for example in a DSP kit, right? So all those trade-offs are there. Okay, So the point to be noted at this point is that as we increase the n, the slope becomes lot sharper, okay, or a steeper, right? Another important point is Butterworth filter does not have any ripples in frequency responses. Okay, no frequency ripples are there. So it's a monotonically decreasing function regardless of the filter order. Okay. Now let's look at some of the properties associated with magnitude square response. First thing is that it's maximally flat at omega equal to 0 because the value is going to be 1. So for the sake of illustration, I have mentioned the square magnitude response expression here. At omega equal to 0, as we all know, if this is 0, then the magnitude square is going to be 1 for all value of n. At omega equal to omega c, magnitude square response is going to be half for all values of n. And magnitude square response decreases monotonically as omega increases. Okay, both in pass band as well as in the stop band region. So what is pass band and stop band region? Pass band region is the range of the frequency as a designer I want to pass through that filter. Stop band region is the range of the frequencies I want to minimize as much as possible in my filter design. Okay, so this pass band stop band region obviously varies depending upon your type of the design specification in your hand. And the fourth one, as I mentioned, the square magnitude approaches to an ideal representation of a low pass filter as n tends to infinity. Now we'll talk about system function of the Butterworth low pass filter. So system function meaning that HA of S. So this is the square magnitude response, okay, of the Butterworth low pass filter. Let me take it back. This is a magnitude square. Okay, so H A j omega magnitude square is nothing but 1 over 1 plus omega divided by omega c to the power of 2n. Now let me try to obtain a system function which is h of s. Okay, so the magnitude square can be put up in this particular fashion. This magnitude square can be written as ha j omega ha conjugate j omega. This conjugate I can remove it by putting a negative sign, which is here. So we know that s is equal to j omega. So ha of s, ha of minus s is going to be 1 divided by, in this expression, omega, I am going to put s divided by j, s divided by j, omega c to the power of 2n. So let us do a simple math. This is 1 divided by 1 plus. So this is 1 over j square, which is going to be minus s square divided by omega c square to the power of n. Now, if you do simplify this, this becomes omega c to the power of 2n divided by minus s square to the power of n plus omega c to the power of 2n. Now, the question is how many poles and how many zeros I have. Okay, clearly I do not have any zeros because here it is not a function of s in the numerator. In the denominator, obviously, I have a function of s. And so I'm going to get a poles associated with this magnitude square response. So the poles of HA of S and HA of minus S is obtained by solving the equation, which is this denominator term to be equal to 0. So how many roots I am going to get? So obviously I'm going to get, because it's S to the power of 2n is there, 2n uh, roots I'm going to get. Like if it is a quadratic expression, so obviously I'm going to get two roots, right? So like that. Okay, so now let me try to solve it. So let me simplify this. This is minus 1 to the power of n, s to the power of 2n is equal to, I'll take this out, so this is minus omega c to the power of 2n. Since it has to have a 2n roots, So minus 1 can be written as e to the power of j 2k plus 1 times pi for k going from 0, 1, so on to 2n minus 1. Now, depending upon the filter order, my location of the poles would vary. Okay. Now, when n is equal to when n is even, when n is even, when n is even, so that means that this becomes positive. So 2s to the power of 2n is equal to minus would be written as e to the power of j 2k plus 1 times pi omega c to the power of 2n. Now, the location of the pole, which we call it as pk, is equal to s is equal to, so this 2n to the power of will become a, this is equivalent to as if you are taking a 1 divided by 2n root. So omega c e to the power of j 2k e to the power of j 2k plus 1 pi divided by 2n. So this I can simplify and make it as omega c e to the power of j. So 2 get cancels out. So this is k pi divided by n plus pi divided by 2n. K goes from 0, 1, so on to 2n minus 1. When n is odd, and when n is odd, then what happens to this term is obviously this negative sign would remain here and this negative sign would remain here. So you don't need to cancel out that, because you have to remember that you need to get 2n roots, right? So I put a minus sign, then s to the power of 2n. Again, this minus 1, I write it in the form of e to the power of j 2k plus 1 pi omega c to the power of 2n. Then if I break this term into two different terms, e to the power of j 2k pi times e to the power of j pi. So e to the power of j pi is minus 1. So this minus 1 and this minus gets cancels out. And finally, the location of the pole is going to be s is equal to, or pk is equal to, the root is omega c e to the power of j 2k pi by 2n, right? So 2 get cancels out. So you get k pi by n. K goes from 0, 1, so on to 2n minus 1. Okay. So depending upon the filter order, the location of the poles for nth order magnitude square Butterworth filter is given by this expression for n is equal to even, for n is equal to odd. Now, what are these in terms of pictorial representation, or in terms of, to be a more technical word, what are these in terms of s plane? Because these are the location of the poles, correct? So this is of a form of a polar form. So r e to the power of j theta form. So that means that it has to, these locations of the poles should form a circle. Okay, so these two n poles, both for n even and odd, are equally spaced around a circle with the radius of omega c in the s plane and are symmetrically located with respect to both real and imaginary axis. This is a very, very important point when we talk about the pole, um, the location of the poles in your S plane for Butterworth low pass filter. Okay. So let me take an example here. I'm going to take n is equal to 4 and n is equal to 5. This is the location of the pole expression. This is the location of the pole for n is equal to 5, and this is for 4. So n is equal to 4, meaning that 2n minus 1, meaning that the k would go from 0 to 7. For n is equal to 5, k would go from 0 to 9, as you can see here. So this is the expression given. All right. So now, if I fill in the values of the location of the poles, so first thing is that this is how the pole 0 um, diagram looks like in your S plane. So in this case, there is no 0. So that's why I have written pole location of h of s and h of minus s. I'm not talking about A subscript per se. This is already written just to indicate that this is an analog filter. So in your S plane, lot of students they don't write what is this and what is this axis. So you have to make sure that you write sigma j omega. This is a continuous omega. N is equal to 4. N is equal to 4. So what you do here is that so it has to form a circle and it has to be symmetric along the real axis, so meaning that whatever happens here should happen here, and and on symmetric on the imaginary axis, whatever happens here should happen here as well. Okay, so how are we going to place 8 poles around the circle in your S plane? So 8 poles, meaning that, so that means that 2 should be there in each quadrant. 1 2 3 4 5 6 7 and 8. Okay, so we place it. So obviously this is conjugate, these two are two conjugate pair, this is again a conjugate pair, this is a conjugate pair, this is a conjugate pair. So that we have to make sure that we have it, because in order to maintain the symmetricity with respect to the real and the imaginary axis. Now if I look at n is equal to 5, so that means that I need to have a 10 poles. Both, again, it has to be symmetric around the real as well as the imaginary axis. Okay, so again it forms a circle with a radius of omega c in both the case. So I need to have a 5 here. Okay, I need to have a 5 here. So 5 meaning that I can have 2 here, I can have 2 here, and then the fifth one has to be here. Similarly, I have to have the same. So again, this and this is a complex conjugate pair, this and this is a complex conjugate pair, this and this is a complex conjugate pair, this and this again. Okay, now I'm not giving you the exact values, because the exact values you can compute and get the actual location of the pole. But to get an intuitive idea of how actually the location of the poles should look like, this is the very intuitive demonstration of showing to you that this is how the location of the poles should be. Later on, the exact value of the location of the poles we will actually compute it. Okay, so the radius is omega c, and each pole, adjacent pole, is separated by an angular frequency of pi divided by n in both the cases. Okay, this I'm going to talk about it in a little bit of time when I try to derive h a of s, which is a system function. Okay, right, so hold on for a second there. Okay, what are the important observations? The first observation is these two n poles of h of s and h of minus s are equally distributed on a circle with a radius of omega c, as you can see, with angular spacing of pi by n radians per second, as I have already mentioned to you. Second thing is poles are symmetrically located with respect to the j omega axis. So meaning that whatever happens here should happen in the same. Then poles cannot occur on the imaginary axis. If the poles are, because obviously we have to come up with a filter which is stable, so poles cannot be on the imaginary axis. And then one of the most important observation depending upon the filter order is when n is equal to even, we do not have a pole on real axis, as opposed to when n is odd, we have a pole on the real axis, which you can see it here. So for n even, no poles on the real axis. When n odd, poles exist on the real axis. Okay. But remember that we are interested in identifying the location of poles for HA of S. HA of S, right? Because I want to design a filter for HA of S. So in order to design a filter of HA of S, I need to make sure that the filter which I'm going to design, system function should be stable and causal. For that, in the S plane, if you recall from your signals and systems, you need to pick the poles on the left hand side of the S plane. So this is HA of S. So that means that the magnitude response gave me a location of poles and zeros. So for n is equal to 4, I said that there are 8. But that corresponds to the magnitude square. But I need to compute only for h of s. Please try to understand this carefully. H of s. So it means that I need to have only 4 location of poles. And I will pick from this specific plot in such a way, I will pick up the location of poles in such a way that the system function which I design is causal and stable. So I'm going to take the poles on the left hand side of the S plane. So the same thing applies here. On the right hand side, this is nothing but h of minus s, which we don't want to design. Okay, so h of s is causal. We need causal and stable. So h a of s should be making sure that omega c to the power of n and s minus pk, and I take all the poles and take the product of that poles on the left hand side of the s plane. Omega c to the power of n is a normalizing factor such that we always get the value 1 at omega equal to 0 for all values of um, n, as well as at the cutoff frequency. Okay, now let me take an example. Okay, so I hope this is clear to you. So what we have discussed so far is we looked at the magnitude square response of the Butterworth low pass filter. Okay, and then we the expression is given. Then we put in some of the values of continuous omega and try to see whether this looks like a low pass filter, and we established that this looks like a low pass filter. And the cutoff frequency, the value is magnitude value is 1 over square root of 2 at omega equal to omega c, and at omega equal to 0 the value is going to be 1, that we have established. And that doesn't vary depending upon the filter order. As we increase the filter order, obviously the slope becomes a lot sharper. Okay, and later on we derive the expression for the location of poles and zeros for the Butterworth low pass filter. Now what I'm going to do is, and then later on we derive the system function expression, and we want a filter which is stable as well as causal. Okay, because obviously those are the two important aspects. We cannot have a system function which is non-causal and also non-stable, because there is no point in designing those types of filters. So that's why we carefully select the location of the poles on the left hand side of the S plane to make sure that we take we make sure that the filter which we are going to design is stable as well as causal. I hope this is clear. I am reiterating the same thing just to make sure that all the students are on the same page. Okay, now let me go back and compute the system function, which is HA of S for a second order Butterworth filter. So here I'm going to get the actual values. Okay, but at this point in time, based on the schematic which we have got, you should have an idea by this time that what should be, how many poles should be there in your magnitude square response for n is equal to 2. So clearly at each quadrant you should have one pole. So there should have one pole. Okay. All right. So we'll talk about that in a little bit of more detail. So for n is equal to 2, this is a regular expression. Pk is equal to omega c e to the power of j pi divided by 2n plus pi k by n. So k goes from 0 to 2n minus 1. So k goes from 0 all the way till 3. So you substitute the value of k is equal to 0. So p naught is omega c, k is equal to 0. This is going to be 0, e to the power of j pi by 4. Then what do you do next? Then k is equal to 1. If you put k is equal to 1, so exactly the same expression, the k is 1, so this becomes pi by 2. So this is omega c e to the power of j 3 pi by 4. Okay. Now, one thing which you have to remember is um, each one of the adjacent poles are separated by pi by n, in this case pi by 2. So this is e to the power of j pi by 4 plus pi by 2, correct? Plus pi by 2. Okay. So if it is pi by 2, so you are adding plus pi by 2. Okay. Now one k, so you get the same. So there are two ways of doing it. One is just you use this expression, okay, or and then get different values of k's. K naught is 0 1 2 and 3. K goes from 0 1 2 and 3. Just substitute, put that values, you are going to get the actual location of the poles. Another one is, that you identify one of them, and then you plus add plus pi by 2, okay, like this, because you know that each poles are separated by an angular spacing of pi by 2, pi by 2 or pi by n. Okay, so this is omega c e to the power of j 3 pi by 4. Now k is equal to 2, so p2 omega c e to the power of j pi by 4 plus pi. This is going to be omega c e to the power of j 5 pi by 4. 5 pi by 4 can be written as 2 pi minus 3 pi by 4. This is nothing but omega c e to the power of minus j 3 pi by 4, which is nothing but p1 conjugate. Then k is equal to 3. So p3 is omega c e to the power of j pi by 4 plus 3 pi by 2. So this is going to be omega c e to the power of j 7 pi by 4. 7 pi by 4 can be written as 2 pi minus pi by 4. So this is going to be p naught conjugate. So one of the most important aspect is what we have identified as the conjugate pair, because we want to make sure that it is symmetric with respect to the real as well as the imaginary axis. So this is the location of your poles for HA of S and HA of minus S. This is sigma, this is j omega. This is very important, which you need to write. Now, as I said, there are n is equal to 2. So there are 4 poles for H of S and H of minus S. So this is 1, 2, 3, and 4. Each pole should be there in each quadrant. Okay, so those are there. Now this is p naught, p1, p2, and p3. So if you recall, so you always start with k is equal to 0 for the location of pole. So you start from an anti-clockwise direction. So this is p naught, p1, p2, and p3. Now p1 and p2 should be complex conjugate pair. So p2 should be p1 conjugate. If I go back, P2 should be P1 conjugate, and then P3 should be P naught conjugate, which is shown here. So the radius is omega c, okay, and then the location of your angular frequency for P naught is pi by 4. Now if you add pi by 2, then what will happen? This will become pi by 4 plus pi by 2 is 3 pi by 4. If you add again pi by 2 for 3 pi by 4, this becomes 5 pi by 4. 5 pi by 4 is nothing but the conjugate pair of P1. Okay, so 5 pi by 4, if you add plus pi by 2, then this will become 7 pi by 4. Again, this is a conjugate pair for P0. So like that, you can cross check whether you are getting the right answer. Okay, now how do I get a system function? So h of s is equal to omega c to the power of n, n is 2 square, divided by the poles on the left hand side of the s plane, s minus p, p1, s minus p1 conjugate. So omega c square divided by s minus, so p1 is nothing but omega c e to the power of j 3 pi by 4, s minus omega c e to the power of minus j 3 pi by 4. So now I'll leave you for you to just to make sure to simplify this. So when you simplify this, this becomes omega c square divided by s square minus 2 omega c s cos 3 pi by 4 plus omega c square. So cos 3 pi by 4 is nothing but minus 1 divided by square root of 2. So h of s is nothing but omega c square divided by s square plus square root of 2 omega c s plus omega c square. Sometimes what we do is that we put it in the form of normalized system function, wherein omega c takes the value of 1 radians per second. So h of s is nothing but 1 divided by s square plus square root of 2s plus 1. Okay. So in this expression, I'm going to put omega c is going to be 1. Okay. All right. So I hope that this is clear to you. Now, what we are going to do here is I'm going to do the same thing. I'm planning to compute the system function uh, for a Butterworth low pass filter for n is equal to 3. So now let's start thinking n is equal to 3 before we go into an actual derivation and trying to get the exact value and compute the actual expression for h of s. What is the first thing which you need to understand? N is equal to 3. That means that there will be 6 poles around the unit circle. Okay, 6 poles. So three on one side, the what three on one side, and another three on the other side of the imaginary axis. So if you have to have a 3 here and 3 here, so what I have to have is on each quadrant I need to have one pole. So that becomes 4, and then that has to be complex conjugate pair. Since n is equal to odd here, as I have mentioned to you, like n is equal to 5, there we have a pole on the real axis. So 1, 2, 3, 1, 2, 3. Total became 6. And then afterwards, what you have to do is that you have to take poles on the left hand side of the S plane to get your H of S. This is what exactly I'm going to do now to get the system function for n is equal to 3. Okay. Okay. Similarly, now we are going to compute the system function for a third order Butterworth low pass filter. N is equal to 3. So we have the expression. So I computed the location of the poles. N is equal to 3, meaning that P naught to P5 value I'm going to get. P naught is omega C. P1 is going to be this expression, P2, P3, P4, and P5. And now P4 is nothing but P2 conjugate. P5 is nothing but P1 conjugate. So what we do here is, I'll explain this later. I'll come back to this expression here. This plot, pole location for h of s and h of minus s for n is equal to 3. So this is sigma. This is j omega. So as I said, again, you start with P naught, okay, and go anti-clockwise direction. P naught, P1, P2, P3, P4, and P5. Now you should know that P2 and P4 should be a complex conjugate pair. So P4 should be P2 conjugate, and then P5 should be P1 conjugate. And this should be obviously is going to be P0 and P3, which is going to be on the real axis. Now, since once you got established this in your mind, then you try to derive this expression. Once you use the actual formula for n is equal to 3, the pole location, you're going to get this. So now what you have established is P4 is nothing but P2 conjugate. Okay. P4 is nothing but P2 conjugate, and P5 is nothing but P1 conjugate. That you know. So you just put the expression, calculate it, get the values, and cross check whether this P4 is P2 conjugate and P5 is P1 conjugate. Once you get that, then what you need to do is you need to make sure that you get up poles on the left hand side of the S plane. So the poles which are located is P3, P2, and P2 conjugate. Okay. So I'm going to write that. So h of s is omega c to the power of n is 3, omega c 3, omega c 3 to the power of 3 divided by s plus omega c, s minus omega c e to the power of j 2 pi by 3. And then this is going to be minus because of the conjugate pair. I do a simple math here. And then finally, I get h of s is equal to omega c to the power of 3 divided by s plus omega c, s square plus omega cs plus omega c square. So this is the system function for the Butterworth low pass filter for n is equal to 3. Now, If I want to compute the normalized system function, just substitute omega c is equal to 1. And then finally, you're going to get this expression as 1 divided by s plus 1, s squared plus s plus 1. Okay. So I hope so far it is clearer to you of what we have discussed. Now, later on, what you can do here is, this is one thing which I have put in. I mean, this is just for our illustration. I'll not go into the detail of this. So, how do you get a system function for n is equal to 4? N is equal to 4, meaning that, let me go back to my video. So, n is equal to 4, meaning that I have 8 volts. Okay. So, 4. So, and it's not odd. So, it means that I do not have poles on the real axis. N is equal to 4. So, I need to have 4 here, 4 here. Okay. So 2 on each quadrant. 2 on each quadrant you can have. And then, so you need to make sure that you have a complex conjugate pair. Calculate, use the location of pole expression, calculate the values. Once you calculate the location of the poles and then actual values, then take the poles on the left hand side of the S plane and then take the product, okay, what we have done before in the denominator, and in the numerator it's going to be omega c to the power of 4, right? So the same logic. So once I solve for it, then this is the expression. So this is s minus p2, s minus p2 conjugate, s minus p3, s minus p3 conjugate. Okay, so you put in the values and you have to do it. So at this point in time, it should come to your mind. Visualization should pop up depending upon whatever is the filter order, and you should start visualizing where the location of the pole should be, and how, depending upon the filter order, and make sure that it is, I try to make sure that the poles are conjugate pair. We know which one should be a conjugate pair. Based on that, you do the math carefully and try to identify the actual relationship and cross check whether your conceptual and theory tells you that particular aspect. Okay, so the conjugate pair has to happen if there is a complex pole. Okay, now, so we now understood how to get h of s. Okay. Now what I'm going to do here is, in order to get me the filter design, I need two important aspects. One is the filter order and omega c. Okay. And these are actually obtained from the um, design specification. So there are usually two cases for the design specification, which either based on my application I want to design, or one of your boss gives you and then he asks you that, okay, come up with a filter which can do the desired specification. Okay. So in nutshell, either if I am the designer, I will design it, or based on my application, whatever I want, I can make sure that I can come up with these expressions. Okay, so expression meaning that uh, these inequalities here and the actual values. Okay, so now the case one is magnitude square should be between 1 divided by 1 plus epsilon square, and should range between 1 divided by 1 plus epsilon square till 1. So that should happen within the omega p, which is nothing but a pass band H frequency. So mod of omega should be less than or equal to omega p, which is your pass band H frequency. In the pass band H frequency, I want to make sure that the square magnitude response is between square magnitude, or magnitude square response is between 1 divided by 1 plus epsilon square and 1. In the stop band region, which is nothing but we call it as omega c, so omega s rather. So this is a stop band H frequency. So mod of omega greater than or equal to omega s, which is a stop band H frequency, which is in this range. I want to make sure that the value is between 0 and 1 over a square. So these values, actual values, would be actually decided by us as a designer. Okay, so this is your design specification given. Okay, now 1 divided by square root of 1 plus epsilon square, this is the minimum pass band magnitude which I want to have in my design. Okay. 1 over A is a maximum stop band ripple which I want to have in the stop band region. So I am okay to have in my design the stop band so in my design the frequency which I want to reject can have a maximum of 1 over A attenuation. Okay. Ideally, I want to have zero. Obviously, all the frequency should be rejected. But obviously, when you design a practical filters, obviously the value cannot go. You cannot completely remove the frequency. You can make sure that you can minimize the unwanted frequency as much as possible. Okay. So that means that this is the case where I am okay to have the amplitude being modified, okay, to some extent in the pass band region. Ideally, again, ideally I want to have one because I want to preserve all the frequency, but you cannot design an ideal filter, so you will have a small band. So upper band is obviously 1, the lower band in the magnitude response is 1 over square root of 1 plus epsilon square. Similarly, in the stop band region, it is actually going, it needs to be actually 0, but I will have a lower band where the value can be between 0 and 1 over e. Now, how do you determine the filter order? There is a proof which we can go through, just for the sake of make sure that the student for this for the to in order to facilitate the student in terms of the conceptual understanding. So I'm not going through the proof here, but if required, we can discuss about that later as well. So the filter order is given by n is equal to half log 10 of epsilon square divided by a square minus 1 divided by log 10 of omega p divided by omega s. So the first important point here is all the values are known to you. Omega p is known, omega s, epsilon is known, a is known, or a square is known. Okay. Note n must be integer. N must be rounded to the next higher integer. In other words, if n is 2.95, you round out to the next higher integer, which is 3. If it is n is computed is 2.000001, still you round out to n is equal to 3. It should be rounded to the next higher integer. Okay, that is the this from the design perspective. Now, this is how the filter order is calculated. If you have omega c, now you need to compute omega c. Omega c, if you want to match the specification at omega p, which in general we do for a low pass filter, then because this is the frequency which we want to preserve, omega c is computed by omega p divided by epsilon squared to the power of 1 over 2n. If you want to match the specification at omega s, then the omega c is given by omega s divided by a square minus 1 to the power of 1 over 2n. So the omega c again depends upon the calculation of omega c depends upon what exactly as a designer you want to do. You want to match the specification at omega p, or whether you want to match the specification at omega s, meaning that you need an exact pass band specification to be there or exact stop band specification to be there. So what we do from a more practical standpoint is, because since it's a low pass filter, so we make sure that we match, because those are the frequencies which we want to preserve. So we make sure that we match to our specification with respect to omega p. Note that note that chosen n is larger than required because 2.3 is there. So we select 3. The specification can be either met or exceeded at either omega p or omega s. So obviously none of the designs are perfect. So since the order is slightly higher than what we have selected, because 2.3 to 3, so obviously there will be a case where it might exceed the specification in your design perspective. Okay. Now, the second case can be the can be in dB. So you are talking in terms of the dB aspect. Okay, so it is, so the magnitude response in dB is when mod of omega is less than omega p, the magnitude response in dB is between minus ap to 0. And then where in the pass band region, in the stop band region, mod of omega should be should be greater than equal to omega s. It should be magnitude response should be less than or equal to minus as. AP is a minimum pass band attenuation in dB, and AS is a maximum stop band attenuation in dB. So now make sure that these are the positive, even though in the specification it is given as negative. When you derive for it, these AP and AS, you need to take a positive value. Okay, 3 dB attenuation. When we talk about, so AP is 3. Do not put AP as minus 3. Okay, if the question is given is in this particular format, then you, if it is minus 3, then you take AP as 3. If it is written 3 dB minimum pass band attenuation, that means that it is 3 dB value as AP. Attenuation means minus, so that's why it's taken care of there in the express in the statement. Okay, now, so how do you get a compute the value of n is nothing but half log 10, then 10 to the power of AP divided by 10 minus 1 divided by 10 to the power of AS divided by 10 minus 1 divided by log 10 AP divided by AS. Again, n must be rounded to a higher integer. Okay. Now, again, if you want to match the specification with respect to omega p, you take omega c is equal to omega p divided by 10 to the power of AP divided by 10 minus 1 to the power of 1 over 2n. If you want to match the specification at omega s, you take this expression. Now, as I said before, from a design perspective, we make sure that we match the specification at omega p. So we take this specific value of omega c. One of the common uh, error, not an error per se, it is just a calculation mistake which the students do. When they use the calculator, they feed in the values, actual values, and then they make a mistake in the calculation. If you make a mistake in the calculation, then everything goes down, meaning that the answers would be wrong. So make sure that in these types of questions or the filter design aspect, make sure that you try to avoid the calculation mistakes as much as possible, because that is a very, very important thing. Okay, so I'll go through one example. Okay, and then we will see how far we can go. Okay, all right. So determine the order n of the Butterworth low pass filter with the following specification. Pass band attenuation should be less than or equal to 1 dB. Stop band attenuation is greater than or equal to 30 dB. So that means that your AP is 1 and AS is 30. Pass band frequency is 200 radians per second. So your omega P is 200. Stop band frequency is 600. So in other words, it's omega C. So your n is nothing but half of log 10 of, this is the expression 10. This is a formula given. So this is just put this formula, put the actual values, and then finally you get 3.7584. So obviously it should be rounded to a higher integer. So you take n is equal to 4. Okay. You take n is equal to 4. All right. Now, so this is how you actually come up with a system function for a low pass filter, which we have discussed. And the in the other portion which we have spoken, what we have spoken is just to make sure that everybody understands is depending upon the specification which is given to us, what we have done so far is we have, whether it's a linear case or a non or a dB case, we have an expression to compute the filter order n and omega c. Okay, so what I'm going to do now is I will going to touch a little bit on digital uh, filters, meaning that it's because digital transformation of these analog filters. Right now we are doing only on H of S, only H of S system function which we are going to design. Then H of Z, correct? Right? So now what we have done is we have a system function which is omega c to the power of n, and then the denominator expression is we can calculate the actual value. But what is omega c to the power of n? That value we don't know, right? So based on the filter order computation and omega c, we can just feed in the values of omega c and n, and then get the actual expression for my h of s, such that it actually does the desired specification. Now, what is a digital transformation of analog filters? So let me touch a little bit on that, and then in the subsequent lectures we will talk about it a little bit more. So digital transformation, so the transformation of the analog filter is nothing but from H of S to H of Z I need to go. There are two different ways of computing it. One is called as a bilinear transformation, another is called as an impulse invariance approach. So in the next class I am going to start discussing about that particular aspect, and moreover I'm going to explain to you in a couple of through with the help of examples how to compute your h of s and h of z given whatever is given in terms of whether it's an impulse invariance approach or a bilinear transformation. These are very important conceptual steps involved. Okay, once if you have understand those those conceptual steps in designing of an analog filter as well as the digital filters through these transformation, then it becomes a lot easier. There are some sequential steps involved. Okay, one, step two, step three, and so on. So if you follow those steps properly, provided you do not do any calculation mistakes, then you are going to get the answer correctly. Okay, let me stop at this point. I hope this lecture was useful. Okay, all right, thank you very much.